Okay, the discovery of the electron. J.J. Thompson, so we're gradually progressing forward in time here, 1856 to 1940. He constructed what was called a cathode ray tube. So this is a glass tube that was partially evacuated. There was some gas in there, but partially evacuated. And then he would apply a high voltage between an electrode at each end of this tube. And he found that a beam of particles, which he called cathode rays, would travel from the negatively charged electrode, which is called the cathode, to the positively charged electrode, which was called the anode. And he called them cathode rays because they started from the cathode. It looked like they were shooting out from the cathode. And so here's a photograph of a cathode ray tube. And this beam here is those electrons. They didn't know what they were. So he found that the particles in that cathode ray had some properties. They traveled in straight lines. They didn't wiggle around. They always traveled in straight lines. The cathode rays were independent of the composition of the material from which they originated. He could make that cathode, the negative electrode, out of different substances. The cathode rays were the same. So that led him to think that this was something that was present in all atoms. And he also determined that they carried a negative electrical charge. That's a fundamental property of some particles. And that results in attractive forces and repulsive forces. And so here's a little summary of what we need to understand about electrical charge. It's a little bit like magnets, which we're more familiar with because you can play with those, right? So a positive charge and a negative charge are going to be attracted to each other. Opposites attract. Two like charges, two positive charges, or two negative charges will be repelled. Just like magnets, you stick them one way and they stick together, and you turn one of those magnets around, and then it becomes very hard to push them together. They repel each other. And these charges come in, well, their magnitudes are integers, basically. We're not talking about measurable charge like coulombs, like physicists or engineers might do. But we're talking about these intrinsic charges, so there's going to be +1 and -1. When you put those two things together, they're attracted to each other, and then overall they have no net charge. So positive and negative charges with the same magnitude will add to 0. So he was able to measure the charge to mass ratio of the particles in this cathode ray by deflecting them. So this is an illustration of what he did. So here, this tube, cathode ray tube, is a little bit different. Here's the cathode and the voltage, and so he's making this cathode ray, and he's got the anode here, but there's a hole in it. And so the beam is attracted to the anode, but then it keeps going through the hole in the middle. So he's shooting this cathode ray, and then he's got a magnet here, and he's got electrically charged plates. And so because they have a charge, he can deflect them using the electrical charge, the electric field. And the magnetic field will also deflect them. And so by measuring the strength of those fields, where's my pointer? The strength of the fields that he applied here, and then looking at how it deflected them, he could measure the charge to mass ratio. So he didn't know what these individual particles were yet, but he was just messing around and figuring stuff out. So he found that the charge to mass ratio was negative 1.76 times 10 to the 8th coulombs per gram. You don't need to remember that number, but there it is. Coulomb is just a unit of charge. So this implied that that cathode ray particle was about 2,000 times less massive than hydrogen, the lightest known atom. So, at this point they're thinking that atoms are the smallest pieces of matter, the smallest pieces you can have. So here he's found something that's smaller than an atom. This was mind-blowing. The indestructible atom can be chipped. It can be, you can knock pieces off of it. And what he had discovered were electrons. Electrons are negatively charged particles within atoms. All atoms have electrons, and all the electrons are the same. And they have a very low mass. And so this was the first the first evidence that all elements are actually made from the same particles. And then Millikan, 1909, here we've got an American, he performed what's now known as his oil drop experiment. And I'm going to just talk you through this a little bit, and then there's a video. From this, he was able to figure out the charge on a single electron. Thompson had found the charge to mass ratio. So what is this funny looking thing? Okay, so up here he's got an atomizer that's spraying out fine, very small droplets of oil. There's a positively charged plate, and these oil droplets are going to fall through a tiny hole in this plate, and they're going to go through a beam of ionizing radiation. And that is going to cause them to be charged. So they get a charge when they hit that beam. So we've got this positively charged plate and the negatively charged plate. We have a light source because it's hard to see in the dark, and we've got a microscope so that you can view. These are teeny tiny oil droplets. Probably can't see them with your eyes, but you can definitely see them with a microscope. So the ionizing radiation gives them a negative charge. A negatively charged particle is attracted to the positively charged plate, and it's repelled from the negatively charged plate. So if you adjust the charges on this, you can get those oil droplets that now have a charge on them to just hang in the air. And from that, he was able to calculate the charge of a single electron. So let's check out this video. This is big video day. I don't always show this many videos.
My name's Billy. I had an epic idea for a prank. Fill a friend's car up with...
In a series of experiments carried out between 1908 and 1917, R.A. Millikan succeeded in measuring the charge of the electron with great precision. In his experiment, a fine mist of oil was sprayed into the upper chamber with an atomizer. Some of the tiny oil droplets fell through the hole in the upper floor, and Millikan was able to determine the mass of an oil drop from its terminal velocity. Next, Millikan used an X-ray source to ionize gas molecules in the chamber. Electrons from this ionization process adhere to the oil droplets. The oil droplets now carry a negative charge. The negatively charged oil droplets can be halted by adjusting the voltage across the two plates. As the voltage across the plates is increased, the velocity of the oil drops slows. As the voltage is increased further, some drops will begin to move upward toward the positive plate. If the voltage is set just right, an oil drop can be suspended. When an oil drop is suspended, its weight, mass times acceleration due to gravity, is exactly counterbalanced by the electric force applied. The electric force applied equals the applied electric field, E, times the charge on the drop, Q. Since the mass of the oil drop, the acceleration due to gravity, and the applied electric field are known, Millikan could solve for Q, which is the charge on the drop. Millikan found that droplets had different charges, but each was a whole number multiple of a smaller charge, equal to negative 1.60 times 10 to the negative 19th coulombs. Millikan concluded that this was the fundamental unit of charge, the charge of an electron. From the charge of an electron and the charge-to-mass ratio of an electron determined by Thompson using a cathode ray tube, Millikan was able to calculate the mass of an electron. The mass of an electron, 9.10 times 10 to the negative 28th grams, is an exceedingly small mass.
The end of that's a little anticlimactic.
This wouldn't be a YouTube channel.
Yeah, sorry, we're not going to watch that one right now. So you do not need to understand how he calculated it. One of the reasons I like to show you a little more about this experiment is because it illustrates how scientists go about finding out this stuff. And that's really what a lot of us find very fascinating is okay, we're trying to figure this out, but we can't just weigh it on a balance or measure it with a ruler or something. It's too small. And so then the puzzle is, how can we figure it out, even though it's something too small for us to see? And so, I mean, you think about 1909, there really wasn't technology. Even electricity was still kind of a new thing. And yet they were doing these very, very cool experiments. Any questions? So he measured the strength of the electric field, and he could figure out the masses, and then he could calculate the charge of each drop. And so he came up with this number because the drops were different sizes, right? He could tell how large the drops were from their radius and their density. And he could figure out the charge on each drop. So the drops are different sizes, meaning they have different numbers of, well, they're going to have different numbers of electrons associated with them and different masses. But when you do ratios again, he came up with this same number, always a whole number multiple of this. So this has to be the fundamental charge of a single electron. And then he was able to calculate the mass of an electron using Thompson's mass to charge ratio. Actually, it was charge to mass ratio, but we need it upside down here.